So 7.6 moment, center of mass, and centroids. Okay. So what we need to do, so first we are going to discuss the definition of mass. Okay. Second is find the center of mass. Okay. And then number 3, find center. This is what we're going to do today. So find the center of mass in two-dimensional system. In 2D system. Okay. 3-dimensional is more complicated. Let's continue. So first, what is mass? A mass is a measure of a body's resistance to change in motion. Mass is a measure of a body's body's resistance to changes in motion. So when something is heavy, we're talking about the mass. If it's heavy and then it's hard to move, it's kind of resistance to changes in motion. Okay, and is independent of the particular gravitational system in which the body is located. Okay, so the mass itself is already there, but if you're going to, for example, if you move some object from the Earth to the Moon, well, the mass itself will not change, but the force probably change. You probably feel it's lighter because the G, the gravitational is different, right? The G is different. Okay, the force on the Earth is 9.8 Newton per kilogram. But on the moon, probably is 1/6 times 9.8, probably 1.5, 1.6 ish, okay, per kilogram Newton. So on the Earth, probably is lighter. You feel lighter for this same object, but it still have the same mass. Okay. So we have the force equals mass times acceleration rate or acceleration. This is AER, acceleration. Sorry. So we have F equals m times a. Or if you take any physics class, you must be very familiar with this formula. F equals ma, and a is the change of the speed or change of speed, instantaneous change of the rate of change of the speed. It's kind of like if you take the derivative with respect to a t. The derivative of the distance, instantaneous rate of change of the distance is the speed. Then, if you take the derivative again, second derivative of that, or the first derivative of the speed, is going to be the acceleration rate. Okay? Then, what is moment? Okay, if x is the distance between the point, and another point. P, the moment of M about the point P is the moment equals the mass times the distance. It's just a definition, okay? We use the big M notation there for the moment, okay? So x is the distance, x is the length of the moment arm. Let's look at an example, a picture. Let's look at a picture. M1 and M2. Okay, 2 points. This is the mass center, and then this is a in the middle. That's the distance. Okay, so you have xy, you have x2. Okay, if m times m1 times x1 equals m2 times x2. If the mass times the distance equals the other mass times the distance times the arm, which we'll call is the length of the moment arm. If this equal, then the system is in equilibrium, so it's balanced. Okay, it will not go to any one point, any side, just even on both sides. Distance has to be bigger than 0. And then the system is in equilibrium point. Okay, so that's just for two objects. M1 times x1 equals M2 times x2. And if we do, we just put x1, x2 on the number axis. For example, this is x. Okay, x coordinate, and this is 0, and then this is the 1, 2, something like that, and this is -1, -2. Okay, on this here, on this number axis, you have a point 0, and you have M2, the second, and then you have M1. You have this point is M3, and you have M4. Okay, so for each one, you also have a x1. So for example, this is x2, and then this is x1. Okay, and then you also have this is x3, and you also have this is x4. Okay, so for each one they have their own length. Okay, so what we have is if M1 x1 plus M2 x2 plus F3 x3 plus, suppose we have more points, plus Mn xn equals 0, then the whole system is in equilibrium. It's pretty simple. Okay. So that's the first definition, mass. We just covered mass, and the next one, we want to look at the moment and the center of mass. Actually, this is not really mathematical thing; it's more physics. Okay. After this section, we're going to move to chapter 8. It's more mathematics. This whole chapter is applying calculus into solving physics problems. Okay, so the moment in the center of mass. So after this section, we're going to move to next chapter of doing just a purely calculus. Okay. So the moment and the center of mass. The moment about the orange point is m0. So m0 equals m1 x1 plus m2 x2 plus mn xm. What does that mean? That means, well, sometimes that moment you add everything together, add m1 times x1, m2 times x1. If you multiply them together, you add them together, it's not zero. The system is not equilibrium. Okay, it's not balanced. So now you have some number here. This m0, you call this one moment. Okay, the moment about the orange point. The center of the mass. So the center of the mass is x bar equals m0 over m. Okay, so then equals m1 x1 plus m2 x2 plus mn xn over m1 plus m2 plus mn. So let's look at one example. Find the center of mass of the point. Find the center of the mass of the point. Mass is lying on x-axis. If we given m1 equals 12, m2 equals 1, m3 equals 6, m4 equals 3, and then what do we have? You get x1. We want to find the center, right? x1 equals negative 6, x2 equals negative 4, x3 equals negative 2, x4 equals 0. Okay, and so we have m5. So m5 equals 11, and the x5 equals 8. Now I want to find out what is the center. What is the center x bar? So I'll give you 2 minutes to do that one by yourself. Use that formula so you can figure that by yourself. The simple one, I would like you to try it by yourself. You apply the formula to find out the center of the mass. Okay, do you get the same thing? You add m1 times x1 plus m2 times x2 plus m3 times x3 plus m4 times x4. So you add all of them, multiply them together, you multiply one by all of them, multiply one by one. Okay, you pair that and multiply it, add together, divide by the total mass, it's going to be the center. Okay? Alright, so let's look at two-dimensional. So for the two-dimensional, we're going to have the point masses have two dimensions, have x and y. Now the point mass m1, m2, until mn be located at x1, y1, and x2, y2, until xn, yn. Okay, and then you have this is two dimension. You have two coordinates: x coordinate and y coordinate. Okay, the position you have two coordinates: x position, y position, and then we define the moment about y-axis, which is y-axis, which is origin point. You can say it's vertical with respect to x-axis, is my equals this if it's y-axis, you are looking in the x direction. So x, this is for example here, x1, y1. Okay, this point x2, y2. Okay, when you look at the what's that called? Like the moment, you are talking about if you have, for example, the weight or the force is going to be this direction, right? If it's the x direction, and then you put it on the x line, then it's the y direction. So the moment about y-axis, my equals m1 x1 plus m2 x2 plus until mn xn. Okay, and then the moment about the x-axis is mx equals is the other direction. So the moment about the x-axis actually is this direction. The object, the force is going this direction. Okay, so you still have like the y. Suppose if it's xy, 1y, and the x2, y2, and then the force direction is going to be that way, because that's your moment direction. This is y-axis, and then you put on the y-axis. Oh, sorry, the moment about the x-axis. So this is the x-axis, symmetric. Okay. But actually, you're working on the y direction, the moment on y direction, because vertical with the x-axis. So mx equals m1 y1 plus m2 y2 plus mn yn. Okay. So the center of x is, you add all the y together, divided by the total mass. Okay, total mass of the object. So mx1, m2. Oh, sorry, it's y1. Because moment of x direction is y plus mn yn. The center of the mass is then m1 plus m2 plus mn. Okay, then the center of y is add all the x moments together. So mx1 plus m2 x2 plus mn xn and then you have the same m1 plus m2 plus mn. Okay, so let's look at one example. Find the center of mass of the given system. Okay, of point mass. So it's 1 point of point masses. So now you have, given it's two-dimensional, you have the m equals 5, 1, 3, and the location for the coordinates x, y is 2, 2, -3, 1, and 1, -4. Okay, now can you use the formula to find out the center for the center of the mass and for x direction and y direction? I'll give you 2 minutes to do that as well. Okay, so I'll write down the answer on the board as well, see if it's the same as yours. Okay, so you again the center for x is x bar. The center of the x direction center is you add 5 times y plus 1 times 1 plus 3 times y. Because it's m1 times y1 plus m2 times y2 plus mn times yn. So basically you multiply the mass and the y coordinates and divide by the total mass, and you get the x center. Okay. So far so good, everyone? Yes? Yep. Okay, great. Okay. Now, so far we have not touched anything of calculus, but the next problem we're going to use the calculus. Okay, we have to use it because it's not going to be a point mass. It's not going to be a point mass, and it's going to be a like a shape, like it's not just 1 point anymore. It's one part of area. Okay, so let's look at the center of mass of planar is called a lamina. Okay, irregular shape, not a point anymore. Consider a irregular shape lamina of uniform density rho bounded by the graph of y equals fx and y equals gx. Okay, so a is less than x, less equal to b, and then we want to find out the center as well. So what do we have? Basically, you're going to have, it's not a point anymore, it's an irregular shape like this. Suppose this is A and this is B. The whole thing is no center. It's not just a point mass. The mass is going to be evenly distributed in this part, okay, in this lamina plane. Okay, so now we want to find out the center for that as well. So first, can anyone tell me what is the formula for the mass formula? So generally, if I give you one shape and tell you the density, so how do I find the area of a particular object? Can anyone tell me that? Mass equals the density. Yeah, is equals the density times the area. Make sense? Okay. So it's rho times the s. Rho times the area is going to be the density times area. Density is just kind of like unit mass of a particular one part. So density times the whole area is the mass of this whole plane. All right. So now, can anyone tell me which part we have to do integration? Density or area? Area, very good. Thank you. Right. So the area, we have to take the antiderivative for the area. So the area, I think we have to do that area in what? At which chapter? So at which section? The first section. We need to find the area between two curves. Okay? If you still remember that. So can anyone tell me what is the area of two curves? What is the area of two curves?
Top curve minus the bottom curve.
So top curve minus the bottom curve. Very good. Suppose this is fx minus gx. Thank you very much. So fx times gx, and then we take the antiderivative from a to b. Okay, so that's very good. That's what we did in the first section. So now we just need to plug in the density into this function here. So now let's look at one. Let's plug it in. So what do we have? Okay. So m about the moment about x-axis. The moment about x-axis, we want to know where. If you look at the formula here, the moment about x-axis, you use m times what? Times y. Okay, use all the mass times the y coordinates. Add them together. Okay. All the moment times the y coordinates. Okay, if you look at this is the my. Okay, so the moment of x is all the m times the y coordinates and divided by the total m. Because the force actually is vertical, it's going if the point like this one is going vertically way and down. So that's how this is y-axis in the middle. Okay. So we have to use question, yes?
Is the density not equal the mass over the volume?
density equals the mass of the volume. Well, we're talking about, you're right, but we're talking about the, we're talking about two-dimensional.
Okay.
Yeah, if it's three-dimensional, that's right. The three-dimensional mass equals rho v, right? Rho times v. But now we're talking about two-dimensional. The third dimension, actually, we consider that just one. We're just not really, we don't consider that we have density times area. Does it make sense? Yeah. Yes? Okay. So it's two-dimensional. We don't have the volume for two-dimensional thing. It's just the area of two-dimensional thing. Okay. So the moment, that's a very good question, Lacey. I'm about the x-axis is we have to use the y coordinates. Okay, so let me just do, I think it's delta m. Okay, so for, let's just look at one particular one. Suppose is we look at this one, the red and the point here. So look at the particular one, delta y here. So first, I want to know the area, the density is given, so just the rho. Well, the moment is m times x, right? So first the density is rho multiplied by the area of the this small thing, the small rectangular. So it's going to be fxi minus gxi. Fxi minus gxi is the length. It's it's the height. It's the height of this. Okay, it's the height of this rectangular. Fxi minus gxi, and then we multiply by the small. Since the rectangular is length times width, you can consider that this is the width, and you have to find out the length. So, can anyone tell me what is the length? So this is the difference, fxi times gxi. So now, what is this one here? What is the length?
dx.
Very good. Thank you very much. Very good. It's dxi. So it's delta xi. Okay. So that's rho times that we have got the what? We got the mass of this small rectangle here. We got the mass here. But now we need to find the moment. So the mass of two-dimensional, the moment is what? The moment is m times x. So the moment of x-axis, the moment of x-axis is the mass times the y coordinates. So we have to times the y coordinates. Well, for this rectangular here, we have two y coordinates. We have a lot. I mean, here this is a one y coordinate. There's a one y coordinate. There's a y coordinate. There's a y coordinate. So here, the y coordinate is changing from gxi to fxi. Okay. Then what do we do for the y coordinates? You can see this pieces of rectangular here. The lowest point of y is gxi. The highest point of y is fxi. So now we don't want to multiply fxi times gxi like all of them, right? So we want to find out since they are even, so we just multiply the y position, which we choose the middle point of y position as the y value. Okay, because you have fxi for here, gxi for here is the y value. So now we just multiply the center one, so it's going to be half of fxi times the gxi, sorry, plus gxi. Okay. This whole thing, this whole thing here is your delta m. Small m is mass. This is y. Okay? That makes much sense. That makes a lot of sense, right? Okay. So now what do we need to do next? We want to put everything, take the antiderivative. Well, it's pretty simple. We get all the xi's, just put a delta x as a dx. That's it. Okay. So the mx and the formula could be just the mx equals from A to B, and the delta x just put up behind. Everything else just take the xi, since we're taking the antiderivative from A to B. So just rho fx minus gx, okay, times half of f, it's too small, just put dx here. Okay, just put everything in, rho times fx minus gx. We don't have I anymore because the I is the integration for a lot of pieces. dxi is going here, dx, and the middle one is half of fx plus gx. Okay, so that's going to be the formula for the two-dimensional. Okay, then in the same way, we also can have my equals in the same way we can have my equals. Can anyone tell me what do you think the my will be? Anyone? Okay, I'll give you a little bit of help. Okay, who wants to try? From A to B, dx, okay, you have, find all the values, so it's going to be A to B, fx minus gx, you still have the rho, okay, and you just have to multiply by the x coordinates. Okay, because that's what you have. You have is my is, this is the for the x for the y coordinate, just because why is that here? Why do we have y is half of the y values, but y is x just have x? Because when you look at this small pieces here, look at this small piece here, the x coordinate is just one line. It's very small, right? Very small piece. So the x is just one line, one level, just one point here. If x equals 2, it's 2 here. If x is 3, it's 3. So we don't have half of x, but y is changing. But x is one level, one point. Okay, because that's really very narrow piece. It's almost very small. Delta x here, so x does not change that much. So we just need to multiply by x. Everything else is the same. Okay, rho times the area times x times dx. Okay. Now we want to find out what is the center. Okay, so the center x bar equals, my bad, I should use big mx. I can't use, because that's for the moment. Because if I use small m, you probably feel like, oh, is that the mass? Actually, it's the moment. Okay, so it's going to be the center is just the moment of x divided by the total mass of that project. Okay, so it's a rho. You can take the rho out because the constant A to B, fx minus gx multiplied by center of x is m. Well, let me see. Center of x is all the y divided by m. Okay, so center of x. Let me see. Did I do anything wrong or not? Okay. So center of x is x dx over rho A to B fx minus gx dx. Okay. So my center is the m of x over x That's right. Okay. And center of y equals rho of a to b and half of fx plus gx times fx minus gx and dx. And the total m is the same, a to b fx minus gx dx. Question?
And I think in the previous notes we have a center of x to be m1 y1 plus m2 y2 plus 2 and then yn divided by all the masses.
Yeah, let me put on the charge here. Let me just see. Okay. In the previous one, we multiply m. Let me see. So the mx1. If you look at the do two-dimensional, so the x. I think it's just a way of saying that my. Okay. Look at the previous one. Look at here. Mxi. Let me just pick. Oh, I think I made a mistake right here. Sorry, my bad. Is x1 here, x2, xn. But it's just a different way of saying that. Is y1. This one is y. Okay. So it's y1, y2, and yn. Okay. Does it make sense now? Lacey?
Yeah.
Okay. Okay. So x bar is still m times x. I think when I do that, I made a mistake there. So now you still have mx. So it's just multiplied by x and over the total mass here. Okay. Total mass of the x. Let's look at an example.
So I have a question.
Yep.
Do we interchange the two diagrams you gave us initially? Is the m of the two diagrams you gave us for the my and the mx? It's on the x and y axis.
You mean the what is given, like the dimensional?
Yeah, the diagrams that at the x-axis and the y-axis.
Yeah, let me give an example. We can see it much better. Maybe next time. Oh, we still have time, right? That's 5 minutes. Yeah, 5 minutes will be enough. Let's look at an example. You will see if you understand. If I answer your questions, okay? The example is find. See if that's answer your question or not. Find x. Sorry, find mx. The moment of x, moment of y, and the center of x and the center of y for phenomena of uniform density rho bounded by the graph of the equation. So the graph should be given to you. You should know the picture. Okay. So the equation will give to you y equals x squared, y equals x cubed, and then if you look at the picture, you're gonna have, and the other one is going to be oh my bad. Not like this. F is bigger is like that, but that is smaller. But x squared is bigger. It's more deep. Okay. Okay. And then the other one is like that. Okay. The red one is y equals x squared. The blue one is y equals x cubed. Okay. So you ask me what is given. Does this question give you and what do you ask for? What's your question, Lacey?
I was actually talking about the first two diagrams you gave us of my and mx, where you were like, that's a two.
You mean here?
Yeah.
Mx m. That's right. My mx m1 x1 plus m2 x2. This is the moment of y, but it is the just add all of them together. It's just the moment about y-axis. It's symmetric to the y-axis, kind of like the idea. So I think that's the definition for the moment of y, but it's still m times x1 times x2, and then the definition is still the center x bar equals the my, the moment of y, over the total of the m, of the small, of the total mass, and the y center is m x over m.
Okay, but there we have like m1 x1 plus m2 x2 for x.
Yeah.
Over.
Yep.
Okay.
Does it make sense now?
Yeah, it does.
Okay. The center is matched with each other. X is x direction, but it's like the name for that is different. Okay. So now let's look at the example, and we're going to finish this example tomorrow, and then we're going to look at chapter 8. Okay. And then if you have questions, you can bring me questions tomorrow as well. And I think we are done with this whole application. So it's more of applying the integration, antiderivative to solve the physics problems, kind of. Okay. And you have your homework online. Just do more practice and apply these formulas to solve those problems, solve the real problems. You should be fine with that. Okay. I'll see you tomorrow. If you have any question, just bring me the question as well. Okay.